Okay, hello everyone. So these are your first video notes for your first assignment for today. This is going to go with Integrated Math 4.1.3. And what I have here is problem 424. Now, this is an extension problem from 423 where you as a class are supposed to collect data, make a scatter plot, make a line of best fit, and then use that to help you answer this question. We're just going to take some pre-slugged data, which can also be found in 424, and we're going to look at that. So all the data is on the scatter plot there that you can see. The line of best fit is already drawn, and I've given you the equation for this line of best fit. And this came from the book, not from me, but this is their equation. The slope is 3.9. and the y-intercept is 63.3. So I want you to look at the graph over here, and you might think, well, wait a second. The line of best fit hits way up above 140. How could the y-intercept be 63.3? Well, I want you to notice that they don't draw a complete graph here. Notice that this is not 0. They cut the graph short. They got 20 and 120 there. So we're not starting at 0. So this equation for the line of best fit is the one that goes right there. So what we're going to look at is the upper and lower boundaries or bounds of where all the data would end up when you have this line of best fit in this set of data. So the first thing you're going to do is you're going to identify the data point that is the farthest away or has the greatest absolute value residual. And look at, they've identified it for us, and I've given you the coordinates of it. The coordinates of that point are 24 and 175. So what we're going to do with that is we're going to first calculate what is that residual. And when we do that, you might remember this from the other day when we were talking in class. Okay, to find that residual, we're going to take x of 24, and we're going to, well, in this case, f for the forearm length, and we're going to put that into our line of best fit, and we're going to see how far away 175, I didn't mean to erase that, 175 actually is from the line of best fit at that expected height right there. So what is that expected height? 424, and then we'll be able to calculate the residual. So we're going to go over here. I'm going to go ahead and change colors. And again, I'm going to try and do this all in one take. So if I make mistakes, I make mistakes. I'll go back and try and fix them. But this is just how I'm going to do it. Those of you who are really into video making, you might hate that I'm going to do it in one take, but I think it shows my human side. Anyway, so I'm going to take 24, and I'm going to put it in for f. So we're going to find out what the expected height, according to this line of best fit, would be for a forearm length of 24. So 3.9 times 24. And then we're going to add 63.3 to that. And so that's going to give us, and use your calculator for this, obviously, 93.6. We're going to add that 63.3 to it, and we're going to get 156.9. So that's what the expected height for someone with a forearm of 24. But the real data that we've got here ended up at 175. So we're now going to calculate this residual, this distance right here, how far that is from the actual line of best fit. Just do that with a simple subtraction where we're going to take 175 and we're going to subtract the 156.9, and we will end up with 18.1. Okay, so that's our residual. That's our greatest residual. And then as we're going to draw the boundaries, you can see those dotted lines. Those are the boundary lines of where all the data will fit within those lines. All the data should fit within those because we took the one that's farthest away. Every other piece of data should fit within those boundaries. We're going to use this for a couple of different things. The first of which is to write the equation of those boundary lines. Okay, so now we already have the equation for the line of best fit. So, and notice that these boundary lines that they've drawn here are parallel. So the equation of them, and let's go with different colors again so that we can kind of see what we're doing here. The equation of them is simply going to be 18.1 above and 18.1 below the line of best fit. So all you got to do with your line of best fit here is add, actually I'm going to get rid of that little thing there. I'm going to add 18.1 to this, and this will give me my upper boundary. I'm going to subtract 18.1 from this. Okay, subtract 18.1, and that'll give me my lower boundary. So when we do that, you will see that our upper boundary equation is going to be h equals, so again, it's going to have the same slope because it's parallel, 3.9 f plus, and then 63.3 plus 18.1 is going to give us 81.4. So 81.4. So that's the equation of the upper boundary. And then we just got to subtract the 8.1 to get the equation of the lower boundary. So the equation of this lower boundary here is going to be 3.9 times the forearm length. In this case, it's going to be plus 45. That's not a very good 45. 45.2. So that's the equation of the lower boundary. So that's the first big key concept there. How do you find the upper and lower boundaries, and what are they? Well, they're parallel lines that are at the max distance one of the data points is away from the line of best fit. So looking at this one here, you can see the blue equation. That's the equation of the upper boundary. The red equation is the equation of the lower boundary. Those are both 18.1 away from the original line of best fit. Now, how do we answer other questions with this? Well, that 18.1 is the key, that greatest residual there. So if we're looking down here at C, it says, using the upper and lower bounds that you just drew, create a range of values for the possible height of a humanoid with a forearm length of 26.4. Well, what we're going to do with that one is, now, I mean, you could just kind of eyeball it and you can kind of look at it. You just zoom in at where is 26.4. Well, it's going to be somewhere in this range, and so you can kind of know about where it's going to be in between. Best, most accurate way to do this, though, is to plug that 26.4 in to your line of best fit to see what the expected value would be, and then just go up 18.1 and down 18.1 from there. So let's go ahead and do that. I'm going to go back to blue. So here we go. So we're going to take H. I'm going to zoom in a little bit. Equals here's my slope, 3.9. And then instead of having F, I'm going to put the forearm length of 26.4 there so we could see what the expected height would be. And I'm going to add 63.3. Okay, so that will give me a total of, there we go, total expected height of 166.26. So multiply that, add 63.3 to it, and you will get 166.26. So that's the expected height. So what would be the range of expectations? Because real data never really is exactly on the line of best fit, or rarely, I should say. So what we do from there is do what we did before, is you just go above that by 18.1. So just add 18.1 to that. So plus 18.1 and minus 18.1. And you could expect the height of this humanoid with a forearm length of 26.4 to be somewhere within that range. So if we were to add 18.1, we'd get 184.36. And if we'd subtract 18.1 from that, we would get 148.16. So we'd expect this humanoid to have a height somewhere in between those numbers of centimeters, and you would put the range to be at, to look like this. So 148.16 is less than the height, and the height is less than 184.36. Now, there's other ways to go about that. I think that's the most efficient way there, but that's how you would do that for this expected range of values for a possible height of a humanoid with a forearm length of 26.4. And that's your first video lesson. Go ahead and do that, the following assignment, and then look at the video lesson for the second assignment, which is going to be really important. Actually, both of these are really pretty important, where we're going to talk about the least squares regression line.